So if you try that one, this is what you do if you have an optimization with a 2 norm, okay, energy. And that one is very simple, channel flow, very boring, okay. And that one is the part, I think Javier talked about that. This is the OR mechanism. This is the best input, and this is what happens to it, okay. And you can see that the input is everywhere, and the output is also everywhere. It fills the entire domain. Okay, because it's energy harvesting. And the best place to harvest the energy is everywhere here. Okay? But now if you say, no, I don't want to have the energy to be harvested, I want to have an infinity norm that localizes the structure in one spot. Okay? If I just get to pick a perturbation that is in one spot, where would that be? Okay? And this is how you do it. P infinity this is the input and this is the output. Okay, so you can localize and really zoom in into parts of the flow field that are particularly prone to localized instabilities. Okay, now this is P infinity. For that one, there is not even an SVD that exists for P to infinity. SVD needs an L2 norm. Okay, energy, eigenvalues need an L2 norm. You have to do optimization if you're interested in anything else than a 2 norm. Okay, so infinity norm, if that's what you want, there's no way, there's no linear algebra that is linked to an infinity norm. This is another recent work that we've done with Max Egel, my student, as now a postdoc in Princeton. This is mixing of a binary fluid. So we were interested in 2D Petri dish of that sort, and then we have 2 cylinders on circular paths, and they go around, and then they mix up the fluid. So we have the blue fluid on the bottom and the white fluid on the top, and if you do everything right, they should all mix together nicely. Okay, and we wanted to optimize that mixing by optimizing the path and the velocity on these circular paths. Okay, so this is exactly the same thing. This is the hydrodynamics. We also have to have an equation for the tracer. This is a nonlinear PDE. We have to do checkpointing. Okay, there's no way around that. This is the adjoint, the sensitivities come out, the optimization, all these things, you should be familiar with now. Okay, so the mixing strategy is what we want to play with. But here is the thing. Mixedness is measured in the best possible way by this norm. So I take the passive scalar, I take the minus 2/3 derivative of it, whatever that means, okay, absolute value, and I integrate over the entire domain, okay? This is a negative Sobolev norm, fractional norm, it's called, okay? And that one, the mathematicians tell us, is the best way of measuring the mixedness of a binary mixture. Okay, this is what we want to optimize because that goes right to the core of mixedness. Okay, no proxy, it does it right away. Okay, so again, this thing is messing up everything. First of all, 2/3 derivatives come into the equations. You have to deal with that thing, and on top of that, there's certainly not a linear algebra SVD that is made for a 2/3 derivative. Okay, it's only for 2. Okay. And on top of that, this is a nonlinear PDE, so we're nonlinear. We cannot even talk about anything about SVDs or eigenvalues. You have to do the optimization. So this is what happens. Okay, this is the path optimization. This is the mixing, and the 2 cylinders don't go through the interface. They actually go back and forth to generate shedding vortices and stopping vortices, and let the vortices do the mixing. That's the best strategy. We would have never guessed that one. Okay, that's a total surprise. We would have thought the cylinders just plunge through it and stir the whole thing up. No, they don't. They just jiggle a little bit in the beginning, send it's like a vortex cannon, right? They send all the vortices towards the interface and let the vortices that they shed do the mixing. That's the best strategy. Okay, and when we saw that thing, look at this. It's a finite time horizon, so they get only to do it a certain amount of time and with a certain amount of energy. Okay, and then they do the mixing. Okay, who would have guessed that? But the nonlinear optimization found that solution, and if you think about it a little bit, it actually makes sense. Okay? You can also do shape optimization. So we turned these things, and in the beginning they all looked like these guys, okay, like hypercycloids. And then we had a certain shape of it. We said, okay, form it any way you want it to do better stirring over one revolution, or I think it's one revolution or two revolutions, I forgot. So let's see how that one does. Okay, so this is an optimized shape for the time horizon with a given rotation speed. Okay, within the constraints. Okay. So you can do anything you want to with that optimization thing. And I realize that this is not stability in the traditional sense, but it certainly uses sensitivity and receptivity and susceptibility information from the adjoint to get the job done. Okay? And you learn about a fluid system by optimizing it and see how it responds, what it likes to do best as you constrain it. This is how you learn about a fluid system. Oops, okay, still turning. Okay, and then on top of that, so this one is basically making modification to this one to go wild, okay? What about additional constraints? You can also say, okay, let this one be energy if you want to, but I have additional constraints that I also want to satisfy. So they would go on the right-hand side, and there's really no limit of what you can add. Okay? So for example, you can say, I want to have a sparse localized stability structure. Then you add a zero norm to here. The optimization gets harder. The adjoint gets harder to evaluate, but it can be done, right? The flexibility is there. You can also have a low-rank stability structure if you penalize it with the nuclear norm. Or you can have some that is the smoothest possible one. Okay? So you penalize the total variation of your initial condition. Okay? And you can throw in anything you want to on the right-hand side. Okay? So for example, you can say, I want to have a structure that is least sensitive to changes in the Reynolds number. So that asks for robustness. Okay? Things of that sort. So the possibilities are almost limitless. Okay. So, in summary, theory over historically has moved from generic flow configurations, right? The days of the Poisson profile are more or less over. Okay, now we're doing DNS and LES and detached eddy simulations. We can do DNS with multi-scale, multi-phase, reactive flows, hypersonics, non-equilibrium, whatever you want to throw in. We can actually simulate these things. Okay, so theory has moved on. CFD has certainly moved on. Same thing with experiments. We started out with hot wires, smoke visualization, Schlieren, very low key, and they still have a place. Okay, but now we also have much more insight into flows from an experimental point of view with Tomo PIV and time resolved PIV and PTV and so on and so on. Okay, and for that reason, I think flow analysis also needs to move on. It needs to move on from looking at eigenvalues and exponential growth and resonance. A good step was already sort of to throw in back that finite time horizon of a stability and redefine stability and move and abandon the Lyapunov concept, which doesn't work so well for fluid mechanics because we have limited timescales. And now go one more step and throw in that optimization-based analysis, realizing that these two things are just special cases. So let's go back to the general case that meshes up with all the things we do in experiments and theory, and then do the stability analysis based on the optimization. So thanks for your attention.
Thank you very much for this excellent lecture. Questions? Who wants to start?
It's not obvious to me how do you define the initial condition for the backward problem? Is there any restriction with respect to the objective?
Yeah, the initial condition for the backward problem is the output of the forward problem. Yeah,
But
that's automatically given. Yeah, that comes out of the derivation.
okay.
So
there's no restriction to the objective.
No, there's no restriction and there's no choice either. There's no choice either. It comes right out.
Okay. Thank you.
Mm-hmm. Yeah.
There.
Yes, there is. There is. So in the question was, can you do that with experimental data when you don't have a governing equation? So the cost objective is still the same. It's what you want. Okay, the constraints are the same, but now the equations will be replaced by conformity to data. Okay, so you will have a data matrix minus the breaking apart into the coherent components. Okay, and you have to basically say that you don't have to stick with an equation. You have to reproduce the data at the end. That's your governing equation, is your data. Yeah. But then you can write down exactly the same thing for data-driven analysis. Yes, there is. Yeah. This was very much model-based, but there's also a data-based version. Yeah. Very good question.
I just wanted to say, first of all, thank you so much. That was amazing talk, and I got a lot out of it. I work in combustion instabilities, and we are exactly in the same, following the same path in the sense that we're looking at modal analysis and linear stability analysis and things. And from the talk, I'm kind of like, wow, we can actually just solve this problem just using brute force, basically. And it opens a whole possibility, so thank you.
Yes,
my question is about how sensitive the adjoint solver is to noise in the flow solution. Could you perhaps do some kind of data compression to basically get around this problem of having to store all the fields for a complex problem?
You can. In that case, you would get a gradient that is suboptimal. So that one is an optimization based on subgradients, it's called. So you can compress the adjoint part, and then get an approximate gradient that points you in the right direction, but not into the perfect direction. So all you do is you sacrifice the accuracy of the gradient, and you have to do maybe a few more loops to really get down to the same optimum. Yeah, but
it's kind of a suck it and see kind of thing. You have to try.
Model reduction. That's one of the things that we're working on now too. Is how can you speed up the adjoint calculation? Do you really need the exact gradient? This is somehow related to, let's say you have a Newton solver and you have a quasi-Newton solver, right? It's the same idea. Eventually you get to the same solution, but the Newton solver gets you the exact steepest descent gradient, whereas the quasi-Newton solver gives you an approximation to the gradient. It's good enough, mostly, especially if you get close. Can we do the same thing with the adjoint? Because the adjoint is a gradient. Can we get away with a few shortcuts on the adjoint and still go to the same minimum? Okay, that's a very good question. Model reduction can be thrown in there. We're playing around with parallelization in time and so on. That speeds up quite a bit the calculation on the adjoint.
Great. I think I have like 50 years of work to do. Thank you.
Me too. Yeah.
Okay, thanks for the amazing talk. The question is, you are going backward in time, and I'm here.
Yep.
And so maybe I missed it, but if I understood well, we are going backward in time because we have taken the original algorithm, the diagram, and then we split it, and then we found that to have it transposed of the Jacobian, we have to flip it.
Yes,
and so
correct.
that's the reason why we're going back.
Correct.
Okay.
Correct. Yes.
But what if we have the Jacobian?
What if you?
We by chance, by magic, or maybe the system is easy enough, or maybe I have a good mathematician, can I have the forward Jacobian itself without, I mean, is it strictly needed to go backward in time, or is it just a shortcut from a numerical point of view? Maybe
it's needed to go backward in time. If you have an evolution equation that is forward in time, the adjoint has to be solved backward in time. That one goes together.
I missed some point, but maybe I can ask you more later.
Maybe
Thank
at the
you.
coffee break. Yeah, I can fill in a little bit more details. Yeah.
More questions? Fabio, you had one also? Oh, try
if you just yell, I can repeat the question.
Yell.
It doesn't work.
I just want to ask a couple of questions, which seems a bit silly. So the first one is about the discrete and continuous adjoint, whether there's a difference between the two.
Yeah.
And how do you guarantee the self-adjointness of some kind of operators in the discrete case? And whether are we obliged to basically resolve the correct equation of the adjoint? We're just optimizing it. So as long as the gradient is going to a minimum, we're not obliged to be mathematically compliant with the operator.
That's correct. Yeah.
And the second,
Yeah.
a bit more concerned with the topic of the lectures. What is your opinion on the reinforcement learning optimization with respect to the adjoint, more classical methods?
Right. Okay. Okay. So the first one, difference between continuous and discrete adjoint. That's sort of a big debate, and it splits sort of the community into two religions in a sense. The continuous one has certain advantages of having specific terms in the equation that can be identified with certain physical processes. The discrete one is just flipping the whole matrix, right? So there's not much that after you flip the matrix that you can still identify as bits and pieces of an equation. The discrete one is much more convenient from a computational point of view. If you just want to get the gradient done to keep your optimization going forward, then the discrete one is a little bit more convenient. Also, the way we compute it is much more convenient. Okay. There's also subtle differences between the continuous and the discrete one that I can go into. The second question about reinforcement. Reinforcement is not using. Reinforcement is using a proxy for the adjoint. Okay, so it's if you do, for example, stochastic gradients or something, then this is getting the same information by many forward problems. Okay? So it's putting together information that the adjoint gives you with different means. Okay. The disadvantage of this one is also that I should mention and should be honest about is whatever optimum we find here is a local optimum. It's not a global optimum, right? But any gradient-based information cannot give you a global optimum, cannot guarantee you one, because most of the time we're non-convex. So we get stuck in a local minimum rather than a global one. And reinforcement learning, depending on how you do it, has a better chance of arriving at a global optimum rather than a local optimum. Yeah, I think that's probably the biggest differences there are. Yeah. One thing we also look into here is doing that optimization derivative-free. Okay, so the technology for derivative-free optimization, which is doing many forward shots rather than a backward shot, is getting so good that the big divide between gradient-based and non-gradient-based derivative-free optimization, the gap is narrowing more and more, and now they're becoming very, very competitive for complicated problems. So that goes in the same direction as reinforcement learning. Yeah. Yep.
One more, and then I think we will have to go.
If the direct problem is periodic, the way we do this flow simulation is we start with an initial condition and then we do certain numbers of periods until it becomes periodic. But when we go backward in time, do we need to, with one periodic, one period, would it suffice for the adjoint problem?
Why is the forward problem periodic?
Well, if we deal with a periodic,
is it periodic in time or is it?
it's periodic in time.
Periodic in time.
So the way we simulate it, usually we start with an initial condition, and then do a certain number of time steps until
is it
becomes
linear in
periodic.
time, or is it linear or non-linear? If it's,
Well,
I think in both cases, the time horizon, if it spans more than one period, allows more solutions than the one that is over one period. So if you have a multiple period forward simulation, you also need a multiple period backward simulation with the adjoint. So the adjoint will not give you the right gradient if you sort of cut that one short and only go over one period. Okay. It's a little bit like a Floquet analysis where, if you have 5 periods, the amplification over 5 periods is not just 5 times the amplification over one period. There are certain solutions that only grow over 5 periods. That are neglected if you only do one period. And it's a little bit like this. Yeah. So the two time horizons have to match.
Okay, so I propose to stop and go to the break. And since we have a very long lunch break, I propose that we shift the next lecture at 11:15. So we recover this 15 minutes, okay? And thanks again to Professor Schmid for this excellent lecture.